Okay, population growth. So what we're going to do with this lecture is we're going to look a little bit further into what exactly goes into populations growing, populations decreasing, things of that nature. So in the last lecture, we talked about population growth, that formula, right? So you've got obviously birth rate minus death rate is going to give you your overall population growth. Positive, it's going up. Negative, we're seeing some decrease. We also talked about the biotic potential. In other words, like the possibility of, if a population is growing in an uninterrupted manner, how many living things, how many individuals in a population can one population sustain, as well as those limiting factors, right? That environmental resistance. So we're going to come back to this too throughout at the end of the lecture. But when we talk about carrying capacity, we're talking about basically the surroundings. How many people can live in a specific space using a specific set of resources without harming the environment? Okay, and this little diagram to the right shows that. You've got your carrying capacity, which is about 1.5 million. And then what you have is this other line that shows the population. Sometimes the population goes above that, and then you'll see a dip, and then you'll see it kind of like snake around that line. Populations very, very rarely exist in straight, perfect lines. So you're going to see it kind of go up and down. Because what's going to happen is you're going to, overuse resources, you're going to deplete resources. The population then will react to that generally by shrinking. And then it'll then rebound back up. Exponential growth. Okay, so when you have a population that just blows up, it continuously grows at a way that's essentially a fixed percentage of its size. And by size, we don't mean the size of the individual, but rather the size of the population. So you have a population that's growing constantly. Like think of exponents, right? 2 to the second, 2 to the fourth, right? Like that's where we're going. You're growing at such a high rate. It is proportional. It is a fixed percentage of how big that population is, but you're going to get a J curve. So when you have a population that just bolts up exponentially, you're going to see that in a J curve. So that's what represents this kind of boom of population. We also have this awesome diagram from your book, and I'm using it because I think it helps to kind of put it in context, I guess, a weird context. So you have that Delphina, right, which is like a little disgusting water bug. And then you have a car. Okay, so if you look at our little water flea there, you have an exponential increase. That population is growing at a very high, rapid, fixed rate. And that's, that because of the J curve, right? Sorry, guys, I was interrupted. So what was I saying? Okay, so you have your water flea, which is growing up exponentially, right? And then you have this car, I guess, which is showing more of a more traditional increase, right? Where you have your slope and it's going up on a steady rate, so that thus the line has a steady slope. What's going to happen is, if organisms have very few limiting factors, they're probably not going to reach their carrying capacity because there isn't one, right? Their environment is just giving and giving and giving. There are very few limitations, and it's just going to explode, like water fleas, right? A lot of times you'll see this with algae. Algae will just take over because it's not in control. We see this also with like invasive species, like species that are not native. Rats are one. Certain weeds are. Boom. Here we go. So what happens after you have this lovely J curve, which you have on that right hand slope, and you can see between around June, it looks like it just kind of takes up. So it just kind of busts up. So what you have something really awesome going on, and that J curve is causing that population to grow exponentially. Boom, nutrients are depleted, and then it busts. The boom bust, right? Kind of like kind of like everything, right? Kind of like populations, kind of like nature, kind of like science, kind of like our economy, kind of like history. This is a cycle that we see very often. So what's going to happen is they'll eventually crash, and then they'll have to restabilize. You then have the logistical growth, right? This is kind of a perfect situation where you have your lovely growth curve. It's like an S, and that K line is going to be the carrying capacity, right? So once the number of individuals hit the carrying capacity, it levels off. Everything is happy in Neverland Forest. So what happens is they do experience growth. They do kind of have an exponential growth, but they stabilize, right? They don't bust. They don't have this huge decrease. They actually they stabilize, and they find a way to live harmoniously in their environment, rather kind of like aggressively, where they population goes up, resources are depleted, it comes down. Population goes up, resources are depleted, it comes down. So logistic growth is kind of like in many ways, it's what we'd like to see, right? So for example, the crabgrass, right? The limiting factor for crabgrass is carbon dioxide. For grass, it's going to be sunlight, right? So you're never really going to run out of sunlight. Carbon dioxide, different story. Okay? All right, so that is it.